Okay, let's start lecture number 27 and we will solve uh, some problems to clarify some concept and how to draw shape force and bending moment diagram. Okay, let's start. Start with a problem, problem 5.11 from the textbook. Draw the shear and bending moment diagram for the beam and loading shown. And second part is and determine the maximum absolute value of the shear and of the bending moment. Okay, so in order to draw or find the shear force and bending moment, so we have to first consider this beam AB as a rigid body, and we have to find what are the reaction at A and what are the reaction at B. It's a simply supported beam. We got two concentrated load at C and E, 300 millimeter from A, C, and E is 300 millimeter from B. And at the center, we have a moment, external moment of 450 Newton meter in uh, clockwise direction. So in order to find reaction at A and B, so if you take sum of forces, sum of moment at B is equal to 0. So if we apply the static equilibrium condition, this condition, so we can find what is the force at A. So let me write the A will be 2.55 kilonewton, and it will be upward direction. And if I take moment about A is equal to 0, so this will lead us to find reaction at P, and that will be 3.45 kilonewton, and the direction will be upward. Now, and by this we will start. Okay, so first we will take a section just before C, coming from A to C, and let's take a section just before this node C. And now if we okay, now before that let's consider point A at A. So shear force V will be equal to 2.55 kilonewton. So let me put 1 over here, and the moment will be equal to 0. Okay, now at the section, now if I write at AC, so let me draw free body diagram. So free body diagram. So shear force V acting downward will take positive, and the moment counterclockwise direction will take a positive. And let me write MV2 and M2. And we have a reaction at A, RA, and this distance, let's take X. Now, sum of forces in vertical direction is equal to 0. So V2 minus RA is equal to 0, and V2 is equal to 2.55 kilonewton. And if I take moment, sum of moment is equal to 0. So this I can write M2 minus RAX, and this will be equal to 0. So M2 is equal to RAX. Now, just before C, when X is equal to 0.3 meter, So this will lead us to M2 is equal to RA is we know that 2.55 kilonewton and multiply by x is 0.3, so that will become say 765 Newton meter. Now if I take a section between C and D, or just before D, so let me take a section just before D, and if I draw a free body diagram just before D, so if I draw a free body diagram, so free body diagram will be, so we have RA, we have a 3 kilonewton of force acting downward over here. So we have shear force. So let me write V3, and we have a bending moment M3. And this distance is x, and this distance will become x minus 0.3. Okay, now considering sum of forces is equal to 0, so sigma f is equal to 0, so this will lead us to V3 plus 3 kilonewton. No, sorry, let me write again. Let me erase this thing and write again. So that will become V3 plus 3 kilonewton minus RA, the value of RA, we know that 2.55, and this will be equal to 0. So V3 will be equal to minus 0.45 kilonewton. So let me again write this thing. So V3 is equal to 0.455 kilonewton. Okay, now for the moment that we are calculating just before T, so moment sigma m is equal to 0, so m3 plus 3 kilonewton into x minus 0.3. Okay, let me write again, sorry about that. M3 plus 3 kilonewton multiplied by x minus 0.3 minus RA. We already know that is 2.55 kilonewton into x. Now, if we put x is equal to 0.5 millimeters, since we are calculating from just before D, so this distance, so that is 0.5. If you put the value of x is equal to 0.5, so M3 we have equal to 675 Newton meter. Okay. Now we will take section just after D, and then we will calculate what will be the value of moment. So we now take a section just after D, and we draw a free body diagram for that. So if I draw a free body diagram over here, just after D, so we have a shear force. Let me write V4, sorry, no, V3. This will be M4. So we have RA, we have 3 kilonewton of force over here at point C, and since we take just after D, so there will be a moment on clockwise direction of 450 Newton meter. Okay, now there is no change in the shear force because there is no shear force acting over there. But however, the value of moment will change. And now if I take moment, sum of moment is equal to 0, so I can write M4 minus 450, right? And again this distance will be x, and since we are taking just after D, so this distance will be remain as x minus 0.2 meter. Okay, now 450, and then we will have minus 450 minus plus 3 kilonewton multiplied by x minus 0.2, and then we have minus for the RA 2.55 into x, and this should be equal to 0. And when we put x is equal to 0.5, so value of M4 will be equal to M4 will be equal to 1125 Newton meter. Okay, now, and the shear force will not change because there is no change in shear force, and that will be equal to minus 0.4 0.45 kilonewton. Now let's take a section. And this will be valid till from now let's take a section from A to B over here. Now we are taking section from right to left just for our convenience. So let's draw free body diagram for this section. And if I draw free body diagram for this section, so we have RB. Now in this case, shear force upward will be positive. Let me write V5, and bending moment in clockwise direction will be positive. And this distance, now we have to be careful, now this distance will become L minus X. L is the total length of the beam and L minus X. Okay. Now obviously at point B, the shear force at point B, the shear force will be equal to reaction at B. And just before E, so we can write V5 plus RB is equal to 0. So this V5 will be equal to RB. We know that we already calculated the value of RB, that is 3.45 kilo Newton. Now for the moment, so sum of moment should be equal to 0. So this will lead us to M5 minus RB into L, the total length of the beam. So that is equal to 300 plus 300, 600, 600 plus 400,000. So let me write 1 minus, so L minus X, so 1 minus X, and this will be equal to 0. Now if X is equal to L, that is point B, so again the moment will be equal to 0. Now if you are interested in E, for E the X will be equal to X is equal to 0.7. So if you put the value, so M5 will be simply equal to RB we already calculated, that is 3.45 L1 minus 0.7, and by putting the value, so M5 is equal to 1125 Newton meter, and that is the same value we calculated for the moment, sorry, the not 1125. So that will be equal to, if you put the value, so my mistake, so this M5 value will be 1035 Newton meter. So that will be 1035 Newton meter. And at B, V, let me write V6, that will be equal to 3.4 kilonewton, and M will be equal to 0, 3.45 kilonewton. Okay, M6 will be 0. Now, these are the internal bending moment and shear force at different location you are interested, and let's plot the shear force and bending moment diagram. Now we calculated the shear force and bending moment at different locations. So and we know the value of shear force and bending moment at different locations. So let's calculate. We'll just draw shear force and bending moment diagram. So we have. So let me draw. Sorry, let me draw over here using scale. So this is my horizontal vertical axis for V, and this is my horizontal axis for the length of the beam. So starting from point A, that is over here, V. So let me write this is in terms of kilonewton. Okay, from we have from A to C, then we have D, and then okay, let me erase this point. Let me draw again this line. So we have point C, we have D, we have E, and then point B. From A to C, the shear force is calculated, that is 2.55 kilonewton. From C, it reduces to minus 0.45, and then it remains constant till E, 0.45, and then it further changes from minus 0.55 to minus 3.45 till B. Okay, now for the bending moment, so the bending moment, we have, let me extend a little bit further. So let me mark, this is C, D, E, and let me put this is B. This is my bending moment in terms of Newton meter. Okay, now from A to C, that is, we increase, and from A to C it's 765 Newton meter. From C to D it decreases a little bit, and that becomes 675. Sorry, let me draw again. From A to B it increases, and it will be 765. Then B to D, there is slight decrease, this is 675. Then just after D is increased to 1125, and then slight decrease till E, 1035, and then from here to B, it is simply 0. From A to it will be simply 0. And the maximum value of absolute maximum shear force is 3.45 kilonewton. Let me write over here max V 3.45 kilonewton, and maximum value of bending moment is 11.25 newton meter. So this is the procedure to draw shear force and bending moment diagram of this problem. Okay, now let's see problem 5.23 from the textbook. So it's an interesting problem. If you look at problem, draw the shear and bending moment diagram for the beam and loading shown. Determine the maximum normal stress due to bending. So for that we have to draw bending moment and shear force diagram of this beam, and we have to find the maximum value of maximum normal stress, and the cross section is given over here. The beam. Now if you look at the beam, this is written as dimension is 7 at 200 millimeter. So total length of the beam is 1400 millimeter, and the distance between AB, BC, CD, DE, EF, FG and GH is equal to 200 millimeters. So total length is 1400 millimeters. Now, if you look at this beam, so at E, we have a hinge. Now, at the hinge, whenever there is a hinge, so the moment at hinge, if I want to write, so ME will be equal to 0. Means there will be no external moment. If there is some external movement, that's okay, but internal movement at E will be equal to 0. And this type of problem we can divide into two sections. So first we will take section EFGH, and we will draw free body diagram to find what will be the reaction at E, because E is a pin joint hinge over there, so there must be a reaction. So if I draw free body diagram for section EFGH, so there is a one reaction at E, and there is external reaction at H, considering rigid body, and we have a force at F that is 40 Newton, and we have another force at G that is 300 Newton. Now we can easily find these forces using static equilibrium condition. So the reaction at E will be equal to 126.67 Newton, and at H it will be equal to 213.33 Newton. How you can find, if you take moment about H, you can find H, and if you take moment about H, you can find the value of E, reaction at E. Okay, now we have to find shear force and bending moment diagram, again following the previous method. So for this section EFGH, so we will find the shear force and bending moment for this section EFGH. So first we take a section between EF. So if I draw section between EF, so that is E, shear force acting downward will be positive and bending moment counterclockwise direction, it will take positive. And now if I take section between F and G, between over here, so this section I can draw like so. This is 40 Newton. Shear force acting downward is a positive. Bending moment counterclockwise direction, anti-clockwise direction is positive. And we have a E over here. Now for the section FG, we will take section from right to left or from H to over here. So if I draw free body diagram for that section, it will be simply H over here, and in this case shear force acting upward will be positive and bending moment in clockwise direction will take positive. Now by applying static equilibrium condition, so I can find the value of shear stresses, shear forces. So shear force, if I want to find between E to F, it will be very simple by applying static equilibrium condition. So we will be simply 126.67 Newton. And between F to G, so V will be equal to 86.67 Newton. And from G to H, shear force will simply minus 213.33 Newton. And it will be constant because there is no distributed load, so it will be constant between these value. Okay, now for the bending moment, if I want to consider bending moment, so let's consider bending moment at F. Let me write at F, considering this free body diagram. So simply M will be equal to, so let me write MF is equal to 0, moment about F is equal to 0, and I can write MF, so sum of moment, MF minus 0.2, that is a distance, and we know the force, that is E we already calculated, that is 126.67, and the moment at F, and that must be equal to 0, and moment about F will be equal to 25.33 Newton meter. Let me remove this one. Okay. Now moment at G, so sum of moment should be equal to 0, so I can write mg, so this will be equal to minus again 0.2, and the force is 213.33, and this should be equal to 0. This should be, let me write over here, this should be equal to 0, and the value of mg will be equal to 42.67 Newton meter. And moment at H will be equal to 0 because, and moment at E is also equal to 0 because these are the pin support. Now we will consider the other section A, B, C, D and E, and we will find the value of first reaction at A. We already know what is E, so we have to find reaction at E, at A and D, and then we will find the shear force and bending moment at different section. Okay, now for external load, so if I draw a free body diagram for section A, B, C, D and E. So free body diagram, we have reaction at A, that is unknown. We have force of 300 Newton at B, at C, so let me put it C, we have a force of again 300 Newton. So at D we have a reaction, and at E the force will be same as we calculated for the previous section, and this force will be acting downward opposite to the previous one. So it will be force is equal to E, and that will be equal to 126.67 Newton. So it's simple to find. So if you take moment about A is equal to 0, you can find D, and if you take moment about A is equal to 0, you will get the value of D, and if you take moment about D is equal to 0, so you will get the value of A. Or you can calculate one taking moment and other is sum of forces in y direction should be equal to 0. Now if you do that, so the value of A will be equal to okay, 257.78 Newton, and the value at D is 468.89 Newton. So these are the forces at A and D. Okay. Now for bending moment and shear force diagram, so we will again considering the shear force and bending moment. It's very simple. Now if I draw a section between A and B, so if just before A and B, and if I draw a section, so it will be simply A acting upward, B will be acting downward, and there's a movement M here. And if I take a section between D and C, so if I draw free body diagram, so A, then we have at B a force 300 Newton, and the shear force acting be positive, and bending moment M is in this direction, will be counterclockwise direction, will be positive. Now And it will be bending moment at D. Now for the between D and E, instead of taking section over here, so we will take section over here, and that will give us the value between C and D. And if I draw full free body diagram for that one, so it will be simple. E will be acting downward over here. So we have shear force acting upward will be positive, and bending moment M will be clockwise as a positive. Now shear forces, it will be very simple. So shear forces between A and B. So we will be 258 Newton. Between B and C, that will be simply minus 43 Newton. You can calculate. And between C and D, it will be constant value of minus 342 Newton. And whereas D and E, it will be uh, 127 or 126.66. Okay. Now the thing is to find the bending moment. So just remember these figures. Just remember these figures, and we will use these figures to find the bending moment for these section. Now we know the sections. Now bending moment at B, we can calculate easily. So bending moment at B. So let me add B. So we can write minus 0.2 to 57.78 and plus MB is equal to 0. So MB is 51.56 Newton meter. But just remember that at A it will be 0, E will be 0, and it will be 0 at D as well, and H it will be 0. Sorry, not it will not be 0 at D. Okay, so it will not be 0 at D, but it will 0 at these points. So let me remove this one. So okay, so this is a moment at B, and starting from A, that is 0 till, and it will be 51.56 at B, and it will be changed linearly. Now moment at C. So if I want to write expression, simply find 0.4, that is the distance, and the value of the force 257.78 plus 0.2 into 300, and this should be plus MC, and this will be equal to 0. So MC is equal to 443.11 Newton meter. Now bending moment at D, so it will not be 0 at D. So bending moment at D we can find it will be simply using the last figure. So MD plus 0.2 into 213.33, and this will be equal to 0. So MD is equal to minus minus 25.33 Newton meter. Now we have the value of bending moment and shear force, and we can draw the shear force and bending moment. So we have the value of shear force and bending moment at different location, so at different sections. So we can draw shear force and bending moment for this beam. So in order to draw shear force diagram, so let's consider this is we have a vertical axis for the shear showing the shear force, and we have a horizontal axis on which along the length of the beam. Okay, V over here, and let me take X. So let's mark this is A, B, C, D, E, F, G, and on the end let's take H. From A to B, the shear force is 258 Newton. From B to C, it's 34 Newton. From C to D, it becomes 342 Newton. And from D to, sorry, this is F, not E. So from that is again becoming 127 Newton. And till F is 127 Newton. From F to G, it's 87. And from G to H, it is minus 213. So this is my shear force diagram. 258 minus 43 minus 342, then 127, this is 87, and minus 213 Newton. Now for the bending moment, so for the bending moment, M over here, and this is X. So again, this is B, C, D, E, F, G, and in the end, let's take this is H. From A to B, it change linearly, and now this is from starting from 0, and from 0 to 51.6, and it will be linear. From B to C, it is from 56 to that become 43.1 Newton meter. Then at T, the value is minus 25, and it will change linearly. And from D to E, it will be 0, and at F, it is 25.3. So it will be 0 at E, and at F it will be 25.3, and it will be a straight line. So let me draw here. This is straight line, and then it will increase 42.7 till G, and from G to H it becomes 0. So maximum value is 51.6. It will be at B. At C it was 43.1. At D it was minus 25.3, and it was 0 at E, and at F it was 25.3. At G it was 42.7, and whereas at H it is 0. So maximum value of bending moment. So if we want to find the absolute maximum bending moment, that is 51.56 Newton meter, and we will use this value to find the stress on this beam. So the normal stress, maximum normal stress, in order to find maximum normal stress, cross section is given. So for rectangular cross section, section modulus S is equal to 1/6 BH square, and we have 1/6. B is 20, H is 30. Sorry, this is 20, 30 square. So section modulus is 3 10 to power 3 millimeter cube, or 3 into 10 to power minus 6 meter cube. So it's normal stress, maximum normal stress. So sigma is, bending moment is 51.56 divided by section modulus, that's 3 10 to power minus 6, and if we calculate, that becomes 17.19 megapascal, and it will, the location of the maximum bending stress will be at E, where we have maximum bending moment. So this is how we draw shear force and bending moment diagram, and to find the maximum value of bending moment, and using that we can find the stress at that location. And by this, these are the assignment problems. So you have to solve all these problems, and you have to submit, online submit these problems to the due date. I will announce the due date on CMatch. Okay, and from the next lecture we will start how to draw shear force and bending moment diagram, or to find shear force and bending moment through graphical method. Thank you.